We have seen that there are different types of convergence for sequence of random variables. Among these convergences, one important type is almost sure convergence. And we have seen also that Kolmogorov 0-1 law has something to do with this kind of convergences. So, here we are trying to explore whether or some kind of characterization of almost sure convergences. That means, under what condition we can say that a sequence of random variable converges almost surely, or is there any conditions that should be satisfied, or is it possible that almost sure convergence implies a set of conditions or can produce some interesting results. So, to answer these questions, we need one important theorem due to Kolmogorov, that is called Kolmogorov's convergence theorem. This actually deals with the notion of almost sure convergence under particular conditions. Another important theorem is called Kolmogorov's 3 series convergence. Actually, this is some kind of characterization, that means almost sure convergence implies a set of conditions. On the other hand, if a set of conditions hold, then almost sure convergence will happen. So, these are the things that we are going to study in this talk, in this lecture, and we will also do rigorous proof of both these theorems, because these theorems not only involves the proof, the line of proof, but the technique of proof is not only interesting, but extremely crucial in the sense that it involves some particular techniques, some kind of manipulation or simplification. Nice techniques are also there. So, we need to understand those techniques and tools in order to master in the theory of probability, or we can apply this later on in many results in probability theory. So, now we are going to talk on Kolmogorov's convergence theorem. As we know that there is one law which is very important, that is known as Kolmogorov's 0-1 law. Now, Kolmogorov's 0-1 law explores that this summation x n either converges almost surely or diverges almost surely, provided x n is a sequence of independent random variables. So, it ensures that either this will converge or this will diverge, but the question is, when can we say that such sums converge almost surely? So, that is the natural question that should come immediately after that. Now, a partial answer to this question can be given by what is known as Khinchin-Kolmogorov convergence theorem, or more popularly known as simply Kolmogorov's convergence theorem, and a complete answer is given by Kolmogorov's 3 series theorem. So, now we will discuss these two theorems, Kolmogorov's convergence theorem and Kolmogorov's 3 series theorem, in order to explore that under what condition this sum of variables, that is summation x n, converges almost surely. Now, note one important thing, that here we are discussing or we are considering only the convergence almost surely. So, the statement of Kolmogorov's convergence theorem is as follows. Suppose x n is a sequence of independent random variables, where with expectation of x n equals to 0 and expectation of x n square equals to sigma square. Now, sigma square must be less than infinity. This is a finite quantity for every n greater than equals to 1. So, naturally sigma square is nothing but the variance of x n for each n. Then we can say that summation x n equals to 1 to infinity converges almost surely if summation expectation of x n square less than infinity. That means, here we need the existence of and a condition relating to the second order moment. So, it is enough to show that this condition, this theorem holds only under the assumption of the existence of second order moments. Now, before proving this Kolmogorov's convergence theorem, we first recall two results which are extremely important, as I have already mentioned in the previous talks. One is the famous Chebyshev's inequality, another is Levy's theorem, which we have already discussed. So, what is Chebyshev's inequality? It is probability modulus of x minus mu greater than sigma t is less than equals to 1 by t square, where expectation of x is mu and variance of x is sigma square. So, here also we assume the moments up to second order, and Levy's theorem states that for a sequence of independent random variables, that is x n, this summation x n converges almost surely if and only if. So, it is a both sided theorem, if and only if summation x n converges in probability. We have already proved this Levy's theorem. Now, we will use these two results to prove Kolmogorov's convergence theorem. So, let us consider the proof. So, first put capital X as summation x k, k equals to n to m. Then naturally, since expectation of x k equals to 0 for every k that is given in the condition of the Kolmogorov's convergence theorem, we immediately have expectation of x equals to 0 and variance of x equals to summation k equals to n to m expectation of x k square, which is nothing but summation k equals to n to m sigma k square. Now, we apply Chebyshev's inequality here. So, for consider one epsilon which is greater than 0 and take sigma as square root of summation k equals to m to n to m expectation of x k square. So, the direct application of Chebyshev's inequality gives us probability modulus of summation x k greater than epsilon, which is equals to probability summation x k greater than, we just adjust sigma in the numerator and denominator. So, sigma times epsilon by sigma, and immediate application gives us less than equals to summation expectation of x k square by epsilon square. So, this is the upper bound that we get. Now, just a little bit of simplification gives us epsilon square into probability of modulus summation x k greater than equals to epsilon less than equals to summation expectation of x k square, let us call less than epsilon cube, if m n both greater than n naught. Now, it is clear that we have the condition that summation expectation of x k square is less than infinity. So, there exists for every epsilon, we can always find one n naught epsilon such that whenever m n both greater than n naught, this condition will hold. Therefore, we immediately get probability that modulus of summation x k greater than equals to epsilon is less than epsilon provided m n both greater than n naught. Now, we can immediately write, it is obvious that summation x k equals to n to m, we can always write this as S m minus S n minus 1. So, probability modulus of S m minus S n minus 1 greater than equals to epsilon is less than epsilon. That means, S n or the sequence of S n is nothing but a Cauchy sequence in probability. And now, we apply Levy's theorem to show, and just direct application of Levy's theorem gives us that S n converges in probability to S, S n converges to S almost surely. That means, summation x n converges almost surely. So, this is the proof of Kolmogorov's convergence theorem, which is extremely important, as I have already mentioned in probability theory. So, this relates to the convergence almost surely for a sequence of independent random variables, and we have used Chebyshev's inequality as well as Levy's theorem in order to prove this theorem. So, this can be considered as a nice application of Levy's theorem. Now, let us move on to the next important theorem due to Kolmogorov again, that is known as Kolmogorov's 3 series theorem. But before doing that, let me introduce one definition that is due to Loew and 2 other results. So, the definition means two sequences of random variables, say x n and y n, are said to be tail equivalent if we can have summation n equals to 1 to infinity probability that x n not equals to y n is less than infinity. So, in that case, these two sequences are said to be tail equivalent. So, it is natural that this 3 series Kolmogorov's 3 series theorem involves this concept. We will discuss it immediately. So, 2 other results one is already known as Borel 01 law, which is let omega script f p be a probability space and a n be a sequence of independent events. Then probability a n occurs infinitely open, that is lim sup of a n equals to 0 if and only if summation n equals to 1 to infinity probability of a n less than infinity, or this probability lim sup a n equals to 1 if and only if summation probability of a n equals to infinity. Another result which is also known as Kolmogorov's inequality, but this Kolmogorov's inequality involves two things, one is lower bound, another is upper bound. Here we are going to use only lower bound, that is why I have stated here only the lower bound part in Kolmogorov's inequality. This states that if x1, x2, xn are independent random variables and expectation of xi square is less than infinity, also another additional condition that modulus of xk is less than equals to c, which is less than infinity, that means xk is a bounded random variable, then defining Sn as summation xi I equals to 1 to n, and for every epsilon greater than 0 we get, it can be shown that probability of maximum of sk minus modulus of sk minus expectation of sk greater than equals to epsilon, this quantity, this probability is bounded below by the quantity which is 1 minus epsilon plus 2c whole square divided by summation sigma k square, k equals to 1 to n. Now, let us state Kolmogorov's 3 series theorem. Suppose that xn n equals to 1 to infinity be a sequence of independent random variables. Now, let us define based on this sequence xn, let us define another sequence, let us denote this by xn dashed, which is equals to xn if modulus of xn less than equals to 1 and 0 if modulus of xn greater than 1. Now, for every n greater than equals to 1. Then the series summation xn converges as if almost surely if and only if the following conditions hold. There are 3 conditions. The conditions are: number 1, summation n equals to 1 to infinity probability of omega such that mod of xn omega greater than 1, which is less than infinity. Second condition is summation expectation of xn prime converges, and third condition is that summation sigma square xn prime, that means sum of variances of xn prime n equals to 1 to infinity is less than infinity. Now, we will prove this theorem. First, assume that these 3 conditions hold. Then by Kolmogorov's convergence theorem, what is C? C implies that summation n equals to 1 to infinity xn prime minus expectation of xn prime converges almost surely, because we are given that sum C actually condition C is summation variance of xn prime less than infinity. Now, condition B states that summation expectation of xn prime converges. This immediately implies that summation xn prime converges almost surely. And now, if we recall the condition A and apply now Borel-Cantelli lemma, it says that probability of modulus of xn greater than 1, that is almost infinitely often, that means modulus of xn greater than 1, this occurs infinitely often, equals to 0. So, naturally modulus of xn is less than equals to 1 almost surely, and hence summation xn n equals to 1 to infinity converges almost surely. So, this part is very easy, quite trivial, just by applying Kolmogorov's convergence theorem and Borel-Cantelli lemma and some other concepts here. So, let us prove the converse part, that is, assume that summation xn converges almost surely. Now, xn converges to 0 almost surely implies that probability modulus of xn greater than 1 occurs infinitely often, and that is equals to actually 0. Now, by Borel 01 law, A is proved. Immediate application of Borel 01 law actually proves A. Now let us prove C, that is, note that to prove C, note that xn, the sequence xn and the sequence xn prime, they are tail equivalent sequences. We have already defined what is the meaning of tail equivalent sequences. Also, it is given that summation xn converges almost surely. So, naturally this will imply that summation xn prime converges almost surely, and if you recall the definition of xn prime, it is clear that xn prime is a sequence of uniformly bounded independent random variables. Now, define Sn prime as summation j equals to 1 to n xj prime. Now, since we have already seen that summation xn prime converges almost surely, then it is immediate that limit of n goes to infinity, probability of supremum m greater than equals to n modulus of Sm prime minus Sn prime greater than equals to epsilon, that is equals to 0. Let us denote this by a 1, that is this is equation 1. And this is immediate, this equation 1 actually immediate consequence of the fact that summation xn prime converges almost surely. Now, we apply the Kolmogorov's inequality, in fact only the lower bound, which immediately gives that probability supremum over m greater than equals to n Sm prime minus Sn prime modulus of that greater than equals to epsilon is greater than equals to 1 minus 2 plus epsilon whole square by summation sigma xj prime square. Now, C here is actually 1. Now, if the denominator, that is summation sum of variances of xj prime is equals to infinity, then probability of supremum of modulus of Sm prime minus Sn prime greater than equals to epsilon equals to 1. Now, remember this actually contradicts 1. So, this cannot be true. So, summation of variance of xj cannot be equals to infinity, because this contradicts 1. So, naturally summation of variance of xj prime, that is summation sigma xj prime square, must be less than infinity, and this actually proves C part or the condition C in the statement of Kolmogorov's three-series convergence theorem. Again, if we apply, if we check that Khinchin-Kolmogorov's theorem or Kolmogorov's convergence theorem, that summation xn prime minus expectation of xn prime converges almost surely. Since it is given that summation xn prime converges almost surely, we also have summation expectation of xn prime converges, and which naturally proves P. So, we have already proved part A, part B and part C. Part A is proved through Borel's 0-1 law. Part B is a direct application of Kolmogorov's inequality, in fact the lower bound of Kolmogorov's inequality, and just by applying Khinchin-Kolmogorov's theorem or Kolmogorov's convergence theorem, part B is proved. So, it is immediately clear that Kolmogorov's three-series theorem is some kind of characterization, or rather both way theorem, that summation, when under what conditions summation xn converges almost surely, and on the other hand if summation xn converges almost surely, we can have three nice conditions. So, we have seen what is the meaning of Kolmogorov's convergence theorem, statement of this theorem, and also Kolmogorov's three-series convergence theorem. And we have also understood the detailed proof of these theorems, and which are extremely important, as I have already mentioned, in the theory of probability, especially in the area of convergence for a sequence of random variables. And mostly this helps us in understanding the almost sure convergences with respect to a sequence of random variables. And also this is important to note that we have used some results, like the concept of similar kind of result of Borel's 0-1 law or Kolmogorov's 0-1 law, and also different concepts like limb sup and limb inf, or the probability or a sequence of events occurs infinitely open. So, all these notions that we have already studied previously, we have also used these notions, and some very preliminary but very important techniques are being used in order to prove this theorem. So, we need to remember these techniques, the techniques of the proof, so that we can apply the same kind of technique later in proving several other results in probability theory and also the convergence related results.